So we talked about earlier this semester about a binomial experiment. That's something that you guys were doing on your exam. That was where you have two possible outcomes, and a lot of times the outcomes were like yes or no, or true or false, things like that. In the next few sections that we're going to talk about, we're going to use multinomial experiments, which is where there's more than two outcomes, is the only difference. Okay, so instead of two possible outcomes with a binomial experiment, we have more than two possible outcomes of multinomial experiment. And those two, or more than two outcomes are going to be our categories. Okay, so categories might be colors or age groups or ways for something to happen, depending on what our survey or experiment is about. The chi-square goodness of fit test is used to determine whether a frequency distribution of whatever our categories are matches an expected distribution. So really what that means is a certain sample of data a good representation of our population? Does our sample represent what should be happening in the population? If I know that my population should give me a symmetric distribution, is my sample also giving me a symmetric distribution? Or if I know that my population is supposed to be, I don't know, spread out a certain way based on percentages, does my sample also have that same sort of spread? So does it represent the population well? Okay. To do the chi-square distribution, we're going to be comparing observed frequencies to expected frequencies. Observed frequencies are what actually happens. So if you do like a survey, your observed frequencies are how many answers you get for each category or how many numbers pop up in each category. Expected frequencies is what you would expect to happen based on maybe population information or previous year's information or data from a former experiment, something like that. So observed frequency is not something you actually have to calculate. You'll be given those or it'll be part of a survey result. Expected frequencies are something that you a lot of times do have to calculate. An expected frequency for any individual category is calculated by n times p sub I, where n is the number of trials or it's the sample size like we've talked about before, and p sub I is the probability of that category happening, whatever that is. So sometimes they'll give you a percentage that you can multiply by n, and that's what we would be using this formula for. Sometimes they'll tell us that frequencies are uniformly distributed, which means they all have the same percentage. So we wouldn't even need to do this. We could just take my n and divide it by whatever my categories are, and that would tell me approximately what each category was supposed to be for its expected probability. So the first thing we're going to do is actually just practice finding these expected probabilities, expected frequencies. And the first one is not on your sheet, so just kind of follow along with me. You don't have to write this down. It says a tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. The results are shown at the right. Find the observed frequency and the expected frequency using the distribution on the bottom there for each tax preparation method. So at the top are the observed frequencies. It's the survey results. So that's actually not really something that we're calculating. It's how many people answered for each category, and here I have 5 categories of ways that their taxes are prepared. At the bottom is what we would expect people to answer. So prior to the survey, the expectation was that 24% of people we're going to use an accountant, 20% we're going to use by hand, 35% by computer software, and those are determined again by like other information from the person that makes the survey, maybe previous year's data, things like that. Those give us our expected frequencies. Write it that way. And here, because we have percentages and they're all different, we're taking our percentage as a decimal and we're just multiplying it by our n value, which here there were 300. So 0.24 times 300. You would expect that 72 people out of the 300 would use an accountant if 24% was the expectation. 0.2 times 300, 60. 0.35 times 300, 105. 0.06 times 300, 18. 0.15 times 300, 45. Once you get your expected frequencies, you can check that that column is correct because it should sum up to your n, which in this case would be 300. So you can double check that all those numbers are right before you then move on to the next step with hypothesis testing that we're going to do in a little bit. Okay, so observed is what actually happened. Expected is what we expect to happen based on data prior to the experiment. And then what we're going to be doing with the goodness of fit test is we're going to see, do those observations, do those samples give us a good representation of the expectation? Do the distributions match? Yes or no? All right, so with your paper now, your handout, you guys have this problem on there. It says the pie chart shows the distribution of healthcare visits for doctor's offices, emergency rooms, and home visits in a recent year. A researcher randomly selects 500 people and asks them how many visits they make, 1 to 3, 4 to 9, 10 or more, or none. What is the expected frequency for each response? Okay, so you have the observed actually you don't have the observed frequencies, but you don't need them here. That's fine. Find the expected frequencies for each, and you can have decimals for expected frequencies. Don't worry about rounding. Let's see how you did. 76.5, 252, 114, 57.5. Sum is 500 at the end. Double check. Any questions? Getting expected frequencies. Cool. Okay. So next thing we're going to do is get to the kind of hypothesis testing part of this. Like we did before with hypothesis testing, you are going to need to, at the beginning, write a null and an alternative hypothesis. And you guys have the steps on your paper there. But this slide here kind of talks about what the null and the alternative are going to look like. And like the previous one that we did back in chapter 7, I think, or no, chapter 9 was the last one we did with the correlations. The null and the alternative are kind of going to always look the same. So the null hypothesis is going to state that your frequency distribution, whatever it is, fits an expected distribution. Okay, so that might be that it is distributed uniformly. Everything has the same distribution. Or it might say something like, you can see the tax prep one that we did a minute ago is listed down here. The expected distribution is going to be 24% by the accountant, 20% by hand, 35% the computer software, 6% of family, and then 15% as tax preparation services. Okay, so certain percentages for each category. The alternative hypothesis is going to say that the frequency distribution does not fit what's expected, just the opposite of that. And so you don't have to be super wordy with these. We don't get too far into them. It just says the distribution of the tax preparation methods is different than whatever is expected. Okay, so it's either the same as what they expect, that's your null, or it's different than what they expect, and that's your alternative. And either one could be the claim. All right, on your paper is this chart here. So here are going to be our steps for our goodness of fit test, which is really going to look like hypothesis testing. So the first thing we're going to do is we're going to have observed frequencies, and we're going to calculate the expected frequencies. Each expected frequency needs to be greater than or equal to 5. If it isn't greater than or equal to 5, then we can't do the goodness of fit test. Also, this will always be a right tail test because of the shape of the chi-square distribution. Remember, you get that really long tail on the right, so you don't have to worry about when you're doing the testing here, is it left-tailed, is it right-tailed, is it two-tailed? It's always going to be a two-tailed test. It's always going to be a positive number you're looking for. We're going to name the claim and the null, the null and the alternative. Level of significance is going to be given to you. Degrees of freedom is k minus 1, where k is the number of categories. Okay, so like in the pie chart, you guys had 4 categories. 4 minus 1 would be 3. 3 would be the degrees of freedom. So we subtract 1 for the degrees of freedom. We're going to find a critical value on our chi-squared distribution table, which is in that packet you guys have. It's table 6. Then we're going to figure out from that critical value where our rejection region is, and then we're going to calculate the chi-squared test statistic, which is as follows. So O will be all of our observed frequencies. E will be all of our expected frequencies. For each category, you're going to calculate the following. O minus E squared divided by E. And then all of those values you're going to sum up. That sum will be your chi-squared statistic. And then we're going to determine, just like our other hypothesis testing, is it in the rejection region or not? If it is, we reject it. If it's not, we don't reject it. And then we summarize our findings. So it either does or does not represent that expected distribution. All right, so we're going to do one of these together on the back of your paper so you can see what these steps look like. It says a researcher claims that the number of different colored candies in bags of dark chocolate M&Ms is uniformly distributed. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown in the table below. At a level of significance of 0.1, we're going to test the researcher's claim. All right, so we're going to start by writing a null and an alternative hypothesis. I'm going to start with my null. Remember, the null is that our distribution, or the distribution in this bag of 500 M&Ms, fits the expectation of what the distribution should be. And the expectation here is that the M&M colors will be uniformly distributed, which means there's going to be a same number of each color, okay? So however you want to word that, I'm just going to say the distribution is uniform of colors of M&Ms in the bag, however you want to say that, okay? And the alternative would be that the distribution is not what's expected, is not uniform. Okay? Which one of those is the claim that the researcher is making? The null. They're claiming that it is uniform. Okay, so over to our table now. We have frequencies. These are the M&Ms that were in the bag. They are observed frequencies. That's our O. The next thing we need is our E, our expected frequencies. Now, here we don't have a percentage, but we know they should be uniformly distributed, which means same number of each color. So if I have 500 M&Ms and there's 6 colors, here our K is 6 categories, 6 colors. You can just do 500 divided by 6, which is going to give us about 83.33. And it's going to be the same for every color. So if we have the same amount of each color in a bag of 500, there would be about 83.33 of each color. Now we rounded a little bit on those, so it won't sum up to exactly 500, but it'll be pretty darn close. Might be off by like a 10th or 2. Actually, like 200ths, I think is all we're going to be off by. Okay, the next thing that you need is you need to do the following calculation. O minus E squared over E. Okay, and this is going to give us our test statistic, the number that we're going to eventually figure out if it's in the rejection region or not. And so you guys are going to do it for each color, and you need your calculators for this. So for brown, I would do 80 minus 83.33. That would be my numerator and square it. Then divide by 83.33. And you should get 0.133. Okay, and then you're just going to do it 5 more times for each color. So for yellow, I would do 95 minus 83.33, square it, divide by 83.33. You get 1.634. 88 minus 83.33, squared, divided by 83.33. 0.262. 83 minus 83.33 divided by 83.33. Oh, shoot, I didn't square it. Hold on. Don't do what I did. Square it, then divided by 83.33. There we go. That one's tiny. 0.001. 76 minus my E square it divided by my E. 0.645, and then 78 is my last one. 0.341. Okay. Sums at the bottom. Again, the sum of your E's would be approximately your N, 500. The sum at the bottom of this test statistics column is going to be our chi squared, which is going to kind of look like a swirly fancy X. Okay, add those all up. 1.634 plus 0.262 plus 0.001 plus 0.645 plus 0.341. And I get 3.016. Okay? Good finding the test statistic. Okay, so now we know the distribution, the shape, is going to look like this. It's going to be a hill on the left, long tail on the right. We need to figure out where the rejection region starts, and that's where you're going to use your table now. Okay, so find table 6 in your packet, chi-square distribution. And at the top is your level of significance, 0.1. And then if my K is 6, what's my degrees of freedom? What's your degrees of freedom? It's just 5. It's one less than your categories. All right, so find degrees of freedom 5 on the left. Go over to level of significance of 0.1, and you guys should see 9.236. And it's always a right tail test. Don't have to worry about pluses or minuses on these. Okay, so now the question is our test statistic, our chi-squared, in our rejection region? Yes or no? It is not in our rejection region, so what does that mean? Do not reject. Okay, so if you were going to summarize your findings, would you say there is or is not enough evidence? Not. My computer's being really slow. Sorry about this horrible handwriting, it's lagging. Not enough evidence. Oh, it's so good. If I plug it in, it's going to be better. To, would we say support or reject? Yes. So to reject, it's a little bit better, the researcher's claim. So we do not have enough evidence to reject the claim that the M&Ms in the bag are uniformly distributed by color. Okay? Make sense? A little bit? Okay, kind of similar to some things we've done before. All right, the last one on your paper there is this guy here. So you guys are going to do the same thing, a hypothesis test with it. Null, alternative. You have survey results, so those are your observed frequency, and this time it's not uniformly distributed. They're giving you percentages that are expected for each category. So you're going to use those percentages to find your expected frequencies, like you practiced on the other side of the paper. Okay, and then once you have the expected frequencies, you can do your calculation for your test statistic, O minus E squared over E. That'll give you your chi squared and so on and so forth. See if you can finish it up then. Okay, so I'll give you guys some time to work this one through, and then this will be the last problem for the day. So you should have, check your E's first, your expected frequencies, and then maybe check your chi squared after that. You should have about 6.7, depending on how you rounded it there. If that number is wrong, you can check each of those littler calculations to get up to it. Your N is 400, categories are 8, so degrees of freedom is 7, with a level of significance of 0.05, degrees of freedom of 7 off of your table should give you 14.067. And then even with rounding there, that chi-square we can see is not in the rejection region, so there is not enough evidence to, in this case, support the claim. Here, double check your null and your alternative. The claim was that the distribution was different than 10 years ago, which means not the same as 10 years ago. So it's because it's that not statement. The claim is the alternative, and the null is that it is the same. That's what we're testing for. Is it the same as this 10-year ago data that we're given? Okay. How'd you do? Any questions? That's it for 10-1. Okay, so let me give you your worksheet that goes along with it. So technically, this is due Friday by the end of the period with your 10-2 worksheet, but you guys can just put it in the tray as soon as you're done with it. It's just 2 questions, 2 hypothesis tests. Okay, so you have a little bit of time today if you want, or you are going to have a work day tomorrow on this as well. Again, it's just all in class. Okay. 1, 2, 3. One of the hypothesis tests on here is a uniform distribution, and the other is not. Looks like your handout. There you go. I'm not going to do cell phone lotto because we don't have any more tests or anything coming up. So you guys don't need to put them over there this week. You can grab them. Can I just do it for fun? I mean, I can tell you if you won or not.
Yeah.
But it's not going to count for anything.
Oh, I know.
All right, let's see. The winner would have been